Now let's talk about how to relax AGM so that we can use MLE to detect communities. Remember, the original AGM assumes binary memberships, and the node is either in the community or not in the community. And we say that it will become a combinatorial optimization problem that's difficult to solve. And here the idea is to relax the binary memberships to real value memberships. Let's say that this FUA here, which is always larger than or equal to 0, is the membership strength of node U to community A. So this is a real number that's always larger or equal to 1. And if FUA equals to 0, then no membership. And we assume that each community A links the nodes independently. So basically PAUV, which is the probability that community A will link node U and node V, is equal to 1 minus the exponential of minus FUA times FVA. So why do we have this? The intuition is that since this function of fx equals to 1 minus exponential of minus x is actually monotonically increasing, and the probability of this connection of u and v is actually proportional to the inner product of these two strings. And what's also nice about this equation is that if one of the nodes does not belong to community A, for example, that let's say that node U does not belong to community A, then FUA will be equal to 0. Then this whole probability will be equals to 0. And following what we have previously discussed, using this one, the probability that at least one common community C links these two nodes, U and V, will be 1 minus the product of 1 minus PC of U and V. So here PC of U and V is the probability that community C will link node U and V. So one minus that is that the probability that this community does not link U and V. And if you have a product of it, that means that basically this is a probability that none of the community will link U and V. And 1 minus that is the probability that at least one common community C will link these two nodes. And note that we can actually write all these different U or FUA using a large community membership strength matrix. For example, in here, we can use each row to represent a node, and we can use each column to represent each one community. For example, let's say this row corresponds to node V, then this entry is actually corresponding to the strength of node V's membership to community A. And also, let's say that this row corresponds to node U, then basically this whole vector here is actually the vector of community membership strengths of node U. And using this large matrix, we can actually write the log likelihood using a matrix formulation. So remember that we say that the community A actually links to the nodes U and V independently. So basically, the probability of them linked together would be 1 minus the exponential of the minus of the inner products. Then the probability that at least one common community C links them will be 1 minus the product of this one. And note that this PC of UV is actually equals to this equation. We can simply expand this using the equation here, and we get this following line. And until now, you might have noticed that this sum is actually equal to the inner product of FU and FV. So basically, using this derivation, we can get the probability of the node U and node V linked together in the matrix form. For example, let's say that we have this small F matrix here, where we have 3 nodes U, V, and W, and we have 4 communities. So basically, this first row is is corresponding to node V, and this is second row. FB corresponds to node V, and this is the third row corresponding to node W. And these are the node community membership strengths. Then if we compute the inner product of FU and FB, we get a number of 0.16. And if you substitute this into this equation, you can calculate the probability that U and V are linked, which is equal to 1 minus the exponential of minus 0.16. And this is equal to 0.14. It's not a large number. And if we look at this F matrix, we can see that the only reason that U and V has a probability of linking together is because they both belong to the 4th community, but the number is relatively small. And similarly, we can compute the probability that node U and node W are connected, and the number is 0.88. And if we look at this F matrix, we can see that the reason that they have such a high probability is that the node U and node W, they both belong to the 2nd community, and the strengths are quite large. And similarly, we can compute the probability of node V and node W linked together. And since if we look at this F matrix, we can find that these 2 nodes actually they don't have any common communities. Therefore, we will set the probability to epsilon. And now the task we have, basically the MLE, will become something like this, where we are given a network G of the set, node set V and edge set E, and we want to estimate a big matrix F. So basically, we want to find an F that maximizes the log likelihood L of F. And this is the log likelihood that we want to maximize, where this P of UV is equal to our old friend 1 minus the exponential of minus the inner product of FU and FV. So if we substitute this into this log likelihood equation, we get our final objective function. So basically, finally, we will try to find a matrix F that would maximize these objective functions here. So basically, for each pair of node where there exists an edge, we will have one term here, which is the log of 1 minus the exponential of minus the inner product. And for every pair of nodes that do not have an edge, we will have another term here, which is just the inner product. So we can see that this is basically a non-negative matrix factorization problem, and we can solve this using a gradient-based approach. But actually, updating this whole large matrix F will take very, very long time, and this is because computing the gradient will take quadratic time. Let's say that we have n node, then basically the time will be n squared. And usually our network are far too big to allow for that. Let's say that you have a network of 1 million nodes, and that basically can have 10 to the power of 12 different edges, and computing this is very, very expensive. So instead, which we choose to update F in small unit. So for example, we can update this FUC for node U while fixing the memberships of all other nodes. And interestingly, we find that we can actually rewrite this log likelihood function as 1/2 sum times the sum of L of FU. So basically this V is the set of all the nodes. And for each of the node U, we will have one term that's called LFU. So specifically this LFU is equal to basically 2 large terms. And this is actually very similar to the original equation. Basically, this is just collecting all the terms about that's related to node U. So if we look at it carefully, you can see that this first large term is related to node U's neighbor. So for every node U, which is for every node V, which is U's neighbor, we will have this one log term. And for every node V, which is not the neighbor of node U, we will have the other term here. And if we substitute the concrete form of P UV, we will get this final equation here. So basically for node V, which is U's neighbor, we have something like this. And for every node V, which is not the neighbor of U, we have something like this. And we find that in order to find this optimal vector FU, we can easily compute the gradient of a single row FU of this large geometric set. So basically, this is the gradient of this objective function with regard to FU. Note that when we're computing this gradient of FU, we're actually fixing all the other FV here. And then we'll use coordinate ascent. And specifically, we will iterate over all the rows of the matrix U. And we will first compute the gradient of the objective function with regard to FU. So this is used to update the row U, right, while keeping all the others fixed. And we'll update the row FU using this equation. So basically, we're using coordinate gradient ascent. We update FU as FU plus the step size times the gradient. And then, because sometimes if you after you update this FU, some value or entries in FU can be smaller than 0, and this is not good. So we will need to project this FU back to a non-negative vector. So basically, if any of the entry is smaller than 0, we will set it to 0. And note that this is actually very slow. And the reason is that computing this gradient takes a lot of time. And why? So this is basically because when you're computing the second term, it actually involves the summation of a lot of FV here, because you always have much more non-neighbors than neighbors. However, luckily, we noticed that this second term can actually be rewritten as something like this. It can be rewritten as the sum of all the F minus FU minus the sum of all the neighbor terms. So basically, one way to compute this second term would be to we can just cache this sum of all the F, and then whenever we're trying to compute some version of this second term, we just need to use this cache version and we will minus FU, and we'll minus the sum of the neighbors. And this saves computation because you always have much fewer neighborhood terms than non-neighborhood terms. And note that the sum of FU actually changes during each gradient descent step, but we can still cache it and update it only every so often. Let's say that we can update it every n steps. So basically computing this second term now takes linear time, and it's linear to the degree of node U. And note that in networks, the degree of a node is much smaller to the total number of nodes in the network. So this is actually a significant speed up